So in our last 28 minutes or so, I want to go over the idea of an infinite geometric series. So we'll do that just by reviewing first, okay? So while you're passing up your homework, I'd like you to finish writing the sentence, okay? Yesterday we derived S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. Finish the sentence. This formula helps us find what? Fill in the rest of the sentence. I'm recording again. So this formula helps us find the sum of the first n terms of any geometric series. Okay, so this brings up a question. What if we want to add up 5 halves, 5 fourths, 5 eighths, and there is no implied ending? It doesn't seem like it stops. Or maybe someone writes it this way. Sigma n equals 1 to infinity, 5 halves to the n. By the way, these are the exact same thing. This goes on forever. You can tell from the infinity up at the top or the dot, dot, dot. Either way, it's going on forever, you can see. But there's obviously no implied ending here. So the first thing I want to ask about this problem is this even meaningful? Do you remember when the child was told to go to the corner of the room and add the numbers 1 through 100? What if the teacher had told the students to go in the corner and add the numbers 1 through infinity? What would the child do? Cry, have a mental breakdown? Or maybe just, if he's smart enough, you just say, that can't be done. Well, can this be done? That's the question. Can this even be done? That's the first thing you should ask yourself. And the way we ask that question mathematically is, does this series converge? Okay? So the everyday way of asking this question is, does this make sense? Or does this even have a sum? This is a thought that should have come to mind. The mathematical way to ask that question is, does this series converge? So what does converge mean? I'm not telling you, I'm asking you. Can you tell from the context of the situation what the word converge means? Probably not going to take any questions right now, Jack. Does this have a sum? Is the same question as does this converge? So what does converge mean? Converge in everyday life are like, light rays that go through a lens and they converge together. Okay? Come together. If we all converge every day right after nutrition or whatever, then we're a third period class. Okay, but that's not quite the meaning in mathematics. So yeah.
Does the series add up to a single value?
That's right. Does the series add up to a single value? Converge means, gives you a meaningful answer. Okay? In this case, it's a sum. We actually use this word converge a lot in math. We use it sometimes to just ask, what are these numbers approaching? Well, these numbers are actually getting closer to 0. So the numbers converge to 0. But my question is about their sum. Can these numbers be packed together to form one meaningful answer or not? The child cannot add 1 through infinity, but maybe the child could add 5 halves, 5 fourths, 5 eighths forever. That's the question. Can he? Is it possible? Does it mean anything? Does it converge? If you think the answer is no, then you would say this series doesn't converge. This series, what? What's the opposite of converge? Diverges. So if you hear the word diverge, what it means is there is no meaningful answer. Diverges. Converges. No meaningful answer. Meaningful answer. Okay, so we got that vocab out of the way a year early. Now, how do we determine if this converges? That is a tough question. But I will guarantee you that this converges. In fact, I can prove to you right now that this converges using a visual proof. The first number here, A1, is 5 halves. 5 halves is half of 5. So imagine a box with area 5.
Let's just pretend it's a perfect square. Okay? I've got a box with area 5. Now I'm going to take that, don't miss this. These are some pretty abstract concepts. It's not a good time to be playing. The first term of that sequence could represent half of this box. There's your 5 halves. And the 5/4 is half of 5, which could be treated as this compartment here, 5 halves. The 5/8 could be visualized as this portion, which is half of the remaining portion. The 5/16, which I never actually wrote, but it would be the 4th term in this, could be represented by half of the remaining section. Now this could go on forever, of course. I could continue to partition the remaining part into halves, and then basically choose one of them, and that would be my next terms. So 5/32 is half of what remains. Okay? So now if I'm asking the question, what do I get when I add all these black numbers together? The answer is 5. So not only do I believe there's a meaningful answer to this problem, I believe I know the answer. I believe the answer is 5. The convergence value is 5. But how do I show work for that? Okay? So here's what you would do. First, you would get out your SN formula. Okay? The formula yesterday was this. This is our formula. We derived it ourselves. Now we wish to talk about very large values of n. In fact, we desire to talk about infinite values of n. Well, the first term is 5 halves in your sequence up above. The r is clearly half. Right? Look at these numbers. They all are half the previous. Right? So this is the best I can do to write down a partial sum formula. It looks like it's just going to be 5 halves, that's first term, times 1 minus half to the n, all of 1 minus half. But what was I hoping to use for n? Infinity. Can I plug in infinity? Can I write S infinity equals 5 halves times 1 minus a half to the infinity all over 1 minus a half? Can I write that?
Yeah, but then you have to do like a limit.
Okay, yeah, we're not really allowed to write these sorts of things because infinity is not technically a number, it's a concept. Right? I remember my friends in high school having all these arguments about infinity. What's half of infinity? What's infinity minus infinity? All of them are dumb questions because infinity isn't a number. Okay, it took me a while to realize the whole question was flawed. So we're playing these games with infinity. Infinity is not a number. You shouldn't be subtracting anything from it. Saying infinity divided by 2 is the same thing as saying cow divided by 2. It doesn't make sense. Or wall divided by 2. It's not a number, folks. It just isn't a number. And if we have equal signs and division symbols and powers, those should all be numbers. So give me a letter, but don't put infinity there. Now you can think this, but never write it. Here's how you write it safely. Okay? You write it like this, so don't miss this, Blake, Jack. You want to write, you can write S infinity on this side, but you want to write LIM, n goes to infinity, and you need to write this up here as just n. So you're not allowed to actually write the infinity in where the n is, but you are allowed to write lim, n goes to infinity, even though it kind of means the same thing. This is the legal, safe way to write it. Nobody will ever get frustrated with you. If you put the infinities in, then mathematicians will say, oh, that looks awful. And they'll get mad at you. Okay? Please don't write it, but write it the way I just did. How do I show that this is 5? Well, the only n in the entire problem is right here. So if I can understand what happens to 1/2 to the n, I can understand what the outcome is going to be here. There's no other n's anywhere. So what happens when you take a half of 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 a half forever?
It's very, very small.
Basically you get 0. Right? 1/2 to the 10th is already very small. 1/2 to the 100th is ridiculously small. And 1/2 to the millionth, which isn't even the end of things, that is so ridiculously small, it's not even worth looking at. So this yellow part will vanish completely if we really let n do its job and go to infinity. So what is the answer to this problem? Just ignore that term. It's 5 halves times 1 over 1 minus a half. Five. Remember, I drew the box and the area was 5 and I predicted that the convergence value was 5. Here's how I can show my work. Okay? So we have one new takeaway today, that if we plan to do an infinite series, we don't need the r to the n part. You see? We don't need that part because it's going to vanish. So here is your takeaway. S infinity is LIM as n goes to infinity of yesterday's formula. But in certain conditions, this is just going to become this. The r to the n will vanish. Now, this will not always vanish, but it will vanish under certain circumstances. Let me ask you this. In this, I'll leave this up for one more second here, so you can copy it. But what was it that caused the r to the n to vanish in that previous problem? Okay, the fact that r was a half, that's why it vanished, right? If r was 52, that term would not have vanished. It would have dominated the problem. Okay? So I'll say that again for those who aren't really listening. Maybe they're still writing. But listen carefully. The reason this term is vanishing is because it's a fraction to a power that's large. If this had been a 2 to the n, we would certainly not ignore it. It would dominate the problem. Okay? But since this was a fraction, it technically vanishes. Okay? Now, do you suppose it would vanish if we had a negative half there? That's worth asking. We're trying to figure out when that r to the n term is going to vanish. So let's take a look at one more problem, then we'll come back to this slide and fill in the rest of the rules for this formula. Let's say that you're given 5 halves minus 5 fourths plus 5 eighths minus 5 sixteenths forever. So notice I put in some extra negatives. Right? I have already shown you that 5 halves plus 5 fourths plus 5 eighths plus 5 sixteenths not only converges, but it converges to 5. I showed you geometrically and I showed you with a limit. So here's my question. Does this up here converge to something meaningful? Can someone give me one good reason why, if this converges to something meaningful, this has to? Yes?
Is it because whenever you're subtracting something, it's smaller than the number that you're subtracting it from, so it can never get bigger?
Good. Excellent. If adding things forever produces a finite answer, say 5, then throwing in some subtraction symbols should certainly only further reduce that value to something less than 5, right? We're literally adding together an infinite number of things, and we got 5. Having some subtractions thrown in there, every other term or whatever, should only further make it converge. In other words, it's going to come out something less than 5. You've got subtractions now, you see? So this is called absolute convergence. If it converges with no negatives, it certainly would converge with a few minus signs thrown in. Don't you agree? It should come out something meaningful and something less than 5. Is that kind of your argument? Very good. Okay, so this is a very important part of next year, all these ideas. And we believe that this will converge. I'm not going to claim I know what it converges to, but I will claim I know it converges. Because of those extra minuses, I believe it would have to converge. So I think it's okay to cross out this r to the n term as long as r is any number between -1 and 1. See, in this first example I did r was a half. In this second example, r is -half. But I believe it converges either way, and I believe this formula holds true either way, because I believe -half to the n would vanish just like half to the n would.
So this formula basically is only good if R is a number between -1 and 1, is what I'm saying. Don't use it if R is 1. Don't use it if R is 3/2. It's only good if you stick to the blue rule up top. So let's go ahead and put that into our box also. This is valid if -1 is less than R is less than 1. Or some people like to write that as absolute value R is less than 1. This is also known as absolute value R is less than 1. Some people like to write it that way. This looks cool. Okay, let's go back to our swinging pendulum problem from yesterday. So in our swinging pendulum problem from yesterday, the bob moved 18 inches across and then swung back. It swung back 17.64 inches, if I remember correctly. It was a, I think it was a 20% reduction. Let me check that problem. Yesterday we did this problem. I want to kind of continue it, you know, so I don't want to have the numbers wrong. Oh, I remember, it was 98%. That's right. So it was swinging across, and then it swung back 98%, and then it would swing back again 98%, which is 14.112 inches. Do you guys remember this problem?
Yes.
Okay. Did I do this problem yesterday? Fourth period.
Not all the way through.
Only in the video. I finished it in the video, okay? But what we saw on this problem was that on the, I think it was on the 10th swing, we figured out how far it swung. We tried to figure out which swing would be only a 12-inch swing or less, and I can't remember which swing it was. And then we tried to find, like, what happens if you add up the first 15 distances. So we actually used our S15 formula for that. So today we'd like to ask the question, if you let the pendulum swing forever, will it actually swing an infinite distance, or will it swing just a convergent, meaningful number? It turns out this thing only swings 900 inches, even if you wait an eternity. So let's see why. So this is like part D. How far does the pendulum bob move in space? If we allow it to swing forever. Whatever that means. Okay, it's just a theoretical question. It's completely hypothetical. Nobody really cares if we can really do this or not. But the answer is cool. So we're trying to find basically S infinity, which we said was A1 over 1 minus R. This formula only holds true if R is a number between -1 and 1. Right? But R was 0.98. R was 0.98, if you remember from yesterday. And the first swing is 18. Look how easy this is to calculate. The answer is simply 900 inches. What does it mean? It means that this thing will move 18 inches, then 17.64 inches, then back 14.112 inches. And if you add up all of those distances, even though there's an infinite number of them, and this goes on forever, there is a convergent, meaningful answer in the end, 900 inches. The pendulum is doing its best to attain 900 inches of travel. That's it. Interesting. Okay, you can also use this idea to write the fractional form of a repeating decimal. Maybe you remember doing this last year, but I want to squeeze this example in because it takes literally a minute, and it's such an interesting conclusion. Some of you know that 0.7777777 is 7/9. Some of you know that. I don't know how you know that, but you know that. Okay, I know that because I've worked with numbers so much. But how would you actually show that? So what you could do is write 0.7 repeating for what it really means. It means 7/10 plus 7/100 plus 7 1,000ths, plus 7 10,000ths, forever. This is how you're going to get all those 7s. Add a placeholder, 0, and then another 7. But do you recognize that this is just a G series? It's just a geometric series. The first term is 0.7, and the R value is 1/10. It looks like you're just multiplying by 1/10 each time. So what I'm saying is A1 is 7/10, and R is 1/10, you see. So now we can use our nifty little formula for today. The sum of all of the terms, every single last one of them, is first term over 1 minus R. Seven tenths over 1 minus 1/10 is 7/10 over 9/10, 7/9. That's cool. We now have a way to convert a rational repeating decimal into its fractional form using the concept of infinite geometric series. That's pretty neat. All you have to do is find that first term and your common ratio. Okay, again, this only works when R is between what two numbers? A1 and 1. If something's growing over time, don't expect it to add up to anything finite, naturally. And if R is 1, then your list would be 0.7, 0.7, 0.7, 0.7, 0.7. That adds up to infinity. And one last little comment. Somebody asked on the way out this morning, what about arithmetic sequences? Do any of those infinite arithmetic ones ever converge? The answer is no. An arithmetic sequence will always diverge. It'll never add up to anything meaningful, no matter what the first term is or the common difference. Only in geometrics and one smaller than it can do this. We'll do something new tomorrow, brand new.